This is the tutorial meant for topic number 7 on magnetostatics. So these questions find the magnetic flux density at the point P in the diagram below. The current in each wire is 2 amperes. So you're given 2 wires, one going out of the page and with a current going out of the page, and the other one with a current going into the page. And then you ask to find the magnetic flux density B at point P. Okay, so if you have a current carrying a wire that's carrying a current I, the easiest way to find magnetic flux density is to apply Ampere's law. Okay, Ampere's law is the magnetic equivalence of Gauss' law. Okay, so the closed loop integral of the magnetic flux density is equals to mu naught I. So in Ampere's law, when you choose the loop, you try to find the loop where the magnetic flux density line is. Okay, so you have to have some prior knowledge about how the magnetic flux density behave. So in a line, we know that the magnetic flux density going to circulate around the line. So that will be the best loop to choose. Okay, so let's say this has a radius r, and if you choose it around that magnetic flux loop, then the magnetic flux is going to be constant. So you can take b out of the integral, and that is equals to mu naught I. And therefore that integral will be equals to 2 pi r, which is the parameters of the circle. It's equals to mu naught I, and therefore b is equals to mu naught I over 2 pi r. Okay, so that's just the magnitude. To find the directions of the magnetic flux, you can apply your right-hand rules. Okay, so the current in that diagram, current is going in these directions, going upwards. So take your right hand, wrap around it, and your fingers that wrapping around it will be the direction of the magnetic flux. So in this case here, it said that the magnetic flux will going counterclockwise. Okay, so that is based on Ampere's law. We know that the magnetic flux density is equal to mu naught I over 2 pi r. So back to these questions. So we have one current. Again, we do it one current at a time, just like how we dealt with the charge in Coulomb's law. We do the same here. Okay, so we do one current or one wire at a time. Okay, so let's look at the one on the top. We have the current flowing out of the page. If I wrap my hand around that, so it's going out of the page. So if I wrap my hand around it, it's going to curve in this direction. So it's going to go counterclockwise. Okay, so we know that the magnetic flux here is going to go counterclockwise. Meaning at P, at point P, the magnetic flux will be this. Okay, because it's going counterclockwise. At a point, it will be the tangent of that point. Okay, so that's where the magnetic flux due to the current on the top. Current on the bottom is going into the page. Okay, so now we wrap around our hand with our thumb pointing into the page. We find that that is going to go clockwise. So at this point, so if I draw a bigger circle clockwise, at this point here, it will be pointing in this direction. Okay, so this is my magnetic flux due to the current going out of the page, no, going into the page, and this is the magnetic flux due to the currents going into the page. To work out the magnitudes of that magnetic flux, okay, so we need to calculate what is this distance here. This is my R. So here is 1 cm separating between them, so this is 0.5 cm. So you can, well, okay, so my R will be square root of 0.5 squared plus 0.5 squared. Or d over 2 squared. Okay, a bit crowded up there. Let me redraw this here. So this is d over 2. So which is equals to half. Here is also half. It's also equals to d over 2. So this distance here will be square root of d over 2 squared plus d over 2 squared. And that should give us root 2 d over 2. So the magnetic flux B will be equals to mu naught I over 2 pi. R will be root 2 d over 2. Okay, so due to the current at the bottom, which is the current going into the page, so the distance from that wire to P again is root 2 d over 2, which is the same distance as the one from the top. And therefore, the flux here is also equals to mu naught I over 2 pi root 2 d over 2. And then you can work out the resultant of, or the sum of the two magnetic flux density. Okay, so B here will be equals to Okay, so we can put the two together. So we're at point P. We have one field going in this direction, which is our B cross, equals to mu naught I over 2 pi square root 2 d over 2. Due to the top wire, we have B the same, mu naught I over 2 pi root 2 d over 2. And if we sum these two vectorially, we know that B will be this. Okay, so this is 45 degree. This is also 45 degree. So you can either write down the unit vector of the black arrow and the unit vector of the blue arrow, or you can use components. So you can resolve this into two components. One component in, if I call this my y and x, so this will be my x component, and this will be my y component. And similarly for the blue one, I also have an x component and then a y component. Okay, so from this, without doing any calculations, we know that the black one is the same magnitude as the blue one. So if we resolve that into the y component, we know that the y component, one pointing upwards, the other one pointing downwards. So they should cancel out. Okay, so this and this is the same, and therefore should resolve into 0. And therefore we can say that this is equals to cos 45 plus cos 45. And then we know that they're both the same, is mu naught so it's twice mu naught I over 2 pi root 2 d over 2 cos 45 degree. Cos 45 is 1 over root 2. Mu naught is 4 pi times 10 minus 7. I is given as 2 amperes. Cos 45 is 1 over root 2 pi times root 2 d is 1 centimeters divided by 2. Put in all this value, you should get 8 times 10 minus 5 Tesla. Based on this example, if you want to put it into vector, B will be equals to 8 times 10 minus 5, and that is in the x direction.